Hi, welcome to this video in multivariable calculus and differential forms. In this video, we are going to be discussing the implicit function theorem, one of the more important theorems in higher level math. Before we dive into the theorem proper, let's just acknowledge the prerequisite topics that we will be making reference to in this video. So there's not really very many. First, we have the inverse function theorem. And this is really going to explain why there's not so much prerequisite knowledge, because most of the information that we are going to be referring to is going to be packed into the inverse function theorem. We'll see that the implicit function theorem is really a pretty natural consequence of the inverse function theorem. So once you've understood the inverse function theorem in terms of what it says and when it can be applied, then really the implicit function theorem will follow readily. But beyond that, we will be making use of general multivariable differentiation knowledge, as well as matrix algebra. So as far as the latter two items are concerned, nothing overly technical, just some general comfortability with these topics is perfectly fine. And as far as the inverse function theorem, well, there's already a video that we've made on this, so you can refer to that if need be, but really all you need to know is when this can be applied and what the result says. With that out of the way, let's start working towards the implicit function theorem. As a preface to the theorem, we are going to start with some motivation that will help ground us in a simple setting that we can understand without the help of the theorem, and then we can go to more general and hence difficult settings where we would require the theorem. But understanding the simple setting first will allow us to get some context for what the point of the theorem, the implicit function theorem that is supposed to be saying and what it's doing for us. So let's start here on the left with an example of a linear function. So linear is simple, basically, and this linear function, this is just an example that we have. It's taking 5 variable inputs, which are notated by w, x, y, z, and t, and it's giving 2 outputs. And you can tell that there's 2 outputs because there's 2 rows to this matrix here on the left, and each row of the matrix corresponds to an individual linear equation. And then we're setting this equal to the 0 vector on the right. The 0 vector has components 0, 0, so what we're doing here is we're asking what are the tuples w, x, y, z, t that satisfy this relationship. In other words, what are the tuples that are zeros of this linear function? So we know how to do that in the linear setting. We have a very simple tool called Gaussian elimination. So if you just do some row operations, you can achieve this equivalent system of linear equations. And so if you just write out the multiplication for what this would mean, then we would have minus 3w plus x plus 2z, then we say that equals 0. And then similarly for the bottom row, that corresponds to the other equation, 8w minus y minus 4z plus t equals 0. So those are the equations that you see here. And what we can do at this point is we can solve for x and for t, because you see x appears alone and only in this top equation, and t appears alone and only in this bottom equation. So due to that, we can isolate x and t, and so we solve for them, and we have that x equals 3w minus 2z, and t is minus 8w plus y plus 4z, just isolating them from their equations here on the left. And so what you can see is that they have become functions of w, y, and z. So what we have here is that x completely depends on w, y, and z, and so does t. T also depends completely on w, y, and z. So they're functions of w, y, and z. So in other words, the zeros of this initial linear equation up here can be expressed in terms of w, y, and z alone, because you just pick anything you want for w, y, and z, and then that induces what x and t are forced to be, because x is forced to be 3w minus 2z, and t is forced to be minus 8w plus y plus 4z. The reason that we were able to do this for x and for t is because when we did this Gaussian elimination here, you can see that we got this submatrix here, which was an identity submatrix. And this corresponded to the variables x and t. Each column corresponds to a variable. And so here's the second column and the fifth column, so corresponding to the second and fifth variables, x and t. And so because of that identity matrix in the second and fifth columns, that's what allows us to solve specifically for x and for t. So usually in a situation like this, we call x and t the pivot variables, and w, y, and z are the free variables. Because like we just said, you're free to pick w, y, and z, and then that constrains what x and t are forced to be. So moral of the story, we can solve for two variables, the pivots, in terms of the other three variables, which are the free variables. Now, it doesn't need to always work out like this. For example, we could have had an inconsistent system at the very beginning, or we could have had some redundancies amongst the linear equations or something like that. But in a general setting where we have that every row of the matrix is linearly independent, then we're going to be in this situation where we are going to solve for pivot variables in terms of free variables. So this is all familiar to us because of what we know from linear algebra. But we want to now extend this in some way to a nonlinear setting. So on the right now, let's take a look at a nonlinear function. So here is a function, which we'll call capital F, of 5 variables. Here we'll just notate them x1, x2, x3, y1, y2. The reason for the notation, right now it doesn't matter. You'll see that it's reasonable choice of notation later on. But in any case, so it's 5 variables, and here is the outputs. So again, 5 inputs, 2 outputs, is indicated by 2 equations here, and it's definitely nonlinear. As you can see, there's multiplication of variables, squaring, cubing, all sorts of things. So not a linear function, but all the same, it doesn't matter. We can still ask, what are the zeros of this function, which we're calling capital F here? Now, because it's not linear, we can't do the same thing that we did over here with, row operations and, pivot variables and everything. But we still want to ask the question, what are the zeros? And the idea is going to be that if there's any solutions at all, so if it's like a consistent system, then there should be many solutions. So there's not going to be a unique 5-tuple that solves this system in general, but instead it should be the case that you are free to pick certain variables, and then that will constrain what other variables are going to be forced to be. And so, as suggested by the notation here, what the point is that if you were to work this example out, then you would find that you can solve for y1 and y2 in terms of the x variables, x1, x2, and x3. So y1 and y2 are both functions of the x variables, x1, x2, x3. Now, the question becomes, how can you actually find the solution? So how can you solve for y1 and y2, because they're all tangled up with the x's, which is in stark contrast to the linear setting when everything's independent of each other. But that is where the implicit function theorem is going to come into play. It's going to say that even if we are unable to explicitly solve for the variables, in this case y1 and y2, we are able to implicitly understand that y1 and y2 are functions of the x variables. We just don't explicitly know what those functions are. So that's the idea behind the implicit function theorem. And in fact, once we introduce the implicit function theorem, we are going to come back to this exact example, and we'll see what the implicit function theorem would say exactly in this situation. That's just some initial context, and now we can go on to state the theorem itself. With our motivation in mind, let's now discuss the formal statement of the implicit function theorem. So, roughly speaking, what this theorem is doing for us is it's giving us conditions under which we can solve for some of the variables in terms of other variables. So, when do we have, pivot variables and free variables when we're setting a function equal to 0? Just like we discussed in our motivating examples. So here is the formal statement. The hypotheses are up here and the conclusions down here. So suppose that we have an open subset of Rn and a function from that open subset to Rm, which is C1, so continuously differentiable. And here we're going to say m is strictly less than n. That is, the output space is of smaller dimension than the input space. So we're squashing space down, again, just like we had in the examples. Viewing Rn, breaking it up as Rn minus m by Rm, so you just kind of isolate the last m variables from the first n minus m, And then points in Rn will be notated x in Rn minus m and y in Rm. So the total point is xy. So if that's our perspective now, suppose that we have a point x bar y bar, which is a 0 of the function, and the partial derivatives of the function with respect to the y variables evaluated at this point is invertible. Those are the conditions under which we can draw our conclusion. Before we get to the conclusion, let's just address this notation for a moment. df by dy, this is representing the matrix of partial derivatives of each of the functions with respect to each of the y variables. There's m functions corresponding to the fact that we are mapping from u to Rm, and there are m y variables. And so we have an m by m matrix here, so it's square, and when you evaluate at this point, the hypothesis is that this is invertible. So if these conditions are true, we have our conclusion of the implicit function theorem, which says then there exists a neighborhood v1 cross v2 of this point x bar y bar. So v1 is the neighborhood part around x bar and v2 is the part around y bar. So in total, this is a neighborhood around the entire point. And to see one function phi from the first part of the neighborhood to the second part of the neighborhood such that this condition holds, which is saying that the function equals 0 and the point is in the neighborhood exactly when y equals phi of x. That is, we can solve for the y variables in terms of the x variables, specifically as dictated by this phi function. So again, the solution is possible for us exactly when the points are in this neighborhood and we are evaluating to 0. So at x bar y bar, we are already assuming that the function evaluates to 0, and we're saying in some small neighborhood around that point, there's going to be points that still evaluate to 0, and for those points, we can solve for the y's in terms of the x's. And then finally, we have this last part here, which is giving us a formula for the derivative of the phi function. Let's just take note of the fact that this phi function, the theorem only says that it exists. We don't necessarily know exactly what this phi function is, hence it's an implicit function. But despite the fact that we might not be able to know exactly what the function is, we can determine what its derivative is, as given by this formula here, and with this derivative, we can give a good approximation of this function phi in a local region surrounding the x bar input. So that's the statement of the implicit function theorem. It looks pretty big. Ultimately, when you understand the idea that it's getting at, it's not so bad after all. It's just giving us certain conditions under which we're guaranteed to be able to solve for some variables in terms of others when our function is set equal to 0. All right, with our new formalized understanding of the implicit function theorem in mind, let's go back to that example that we were discussing in the prior slide and see how we can apply the theorem in that case. So now that we've seen the formal statement of the implicit function theorem, let's see how it applies in this example that we were taking a look at from a few slides ago. So here is the somewhat familiar function. It is of 5 variables, x1, x2, x3, y1, y2, and here are the particular function outputs, and we're setting it equal to the 0 vector. So each individual function set equal to 0. And we're asking what are the zeros of this function. So we start with this point here, which is a particular 0 of this function. So it's 2, 1, 1, minus 1, 1. Just to be clear, this part is the x bar, and then this part is the y bar. You can notice that, for example, if we were to plug this into the bottom equation, we would have, so x1 times x2 times y1, so that's 2 times 1 times minus 1 is minus 2, and then minus x3, y2, so minus 1 times 1. So we have minus 2, minus 1, so that's minus 3, and then plus 3, so you get 0. So okay, so that evaluates to 0, and similarly, if you plug this into the top, you'd also get 0. And now we need to check certain conditions on the derivative of the function. So let's differentiate the function. Here's the derivative. We won't go through the entire thing, but this is just the matrix of partial derivatives. Technically, we need to make sure that this is a continuously differentiable function, but we're dealing with polynomials here. There's no worries about that. We're not at all concerned with being differentiable or continuous. Polynomials are far stronger than that. So definitely all you have to do is just take the matrix of partial derivatives, and that'll give you the total derivative here. So just for example, if we were to differentiate the first function with respect to x3, so if we go up here, the first function with respect to the x3 variable, x3 only appears in this term here, so the derivative here is minus 2x3, and everything else zeroes out, so you just have minus 2x3, and indeed that is exactly what you see in this entry here. So similarly, you just take the partial derivatives of each of the functions with respect to each of the variables. That gives you this total derivative, and then when you evaluate it at the particular point x bar, y bar, this is the matrix you get. And now the idea is we want to try to solve for the y variables in terms of the x variables. Is that possible? Well, if you take a look at this submatrix here that we've highlighted, this is the submatrix of partial derivatives indexed by the y variables, and it is invertible. As you can see, the determinant is non-zero, and so therefore the implicit function theorem tells us that we can solve for y in terms of the y variables in terms of the x variables as given by some function phi locally around that point x bar, y bar, which we were evaluating at. And while we might not know what that function phi is explicitly, we do know what the derivative would be, and in particular the derivative at the x bar point. So to be given by this formula here, as we mentioned on the prior slide. On that prior slide, we had the notation x phi of x. Here we have x bar, y bar. That's because while we don't know the phi function in general, we do know that phi of x bar equals y bar. That is the one point that we do know how to evaluate phi at. So anyway, so this is the same thing. It's x bar, y bar here. Point being, you just take these matrix of partial derivatives in this particular way, do the inverse and the minus and the multiplication, and you get a result. So here, this part is this submatrix, and this part is this submatrix of partial derivatives. And so overall, if you just plug everything in, then you do this multiplication, this is the end result that you get in terms of the derivative of phi evaluated at x bar. And hence, even though we don't know what the phi function is, we can use this to give an approximation of the phi function in some small local region around x bar. So just to reiterate, we now know that we can solve for the y variables in terms of the x variables because this matrix here, this submatrix of partial derivatives, was invertible. So this tells us that we can solve for y1 in terms of x1, x2, and x3, and we can also solve for y2. So in fact, let's just say that y1 equals the first phi function, so phi1 of x1, x2, and x3, and y2 equals phi2 of x1, x2, and x3. So then overall we have y equals phi of x when you consider the total collection here. Now one final important note to bring up is that here we solve for the y variables in terms of the x variables, but the implicit function theorem is a bit more flexible than what we've done here. What it says is that for any submatrix for which we have an invertible derivative, we can solve for those variables. So what I mean is, if we were to erase all this and just clean this up a little bit, so if instead of looking at this submatrix, maybe instead we looked at this submatrix, let's say here. So this submatrix is 2, minus 2, minus 3, 2, and it is indexed by the variables x2 and y1. That's because this portion was the part for taking the partials with respect to x2, and this is the part for taking the partials with respect to y1. So that's what gives us this submatrix, and the determinant, again, is non-zero, so this is also invertible, and so therefore we can also solve for these variables in terms of the other ones. So we could have solved for x2 as some function of so let's just say x2 is some function of x1, x3, and y2, and similarly y1 is some function of x1, x3, and y2. So in general, whenever you have variables that index an invertible submatrix, so it could have been the one that we chose, or it could have been this new one that we're talking about, or whatever, as long as it's invertible, you can solve for those variables in terms of the other variables. So hopefully this illustrated how we can interpret the theorem in light of a specific example, and we will go on to give a couple more enlightening examples before we finish this video up, but before we do that, let's give the proof of this theorem, which we'll see isn't actually so bad once we are already making use of the inverse function theorem. So without further ado, let's go to the whiteboard and give the proof of this theorem. All right, so here we are at the whiteboard, and we're going to go through the proof of the implicit function theorem. So just at the top here are the given hypotheses that we start with, which is that we have a function which goes from Rn to Rm, as given here, and Rn we're breaking up in this way again. It's the latter m components and then the former n minus m components. And this is a C1 function, and we have a particular point of the function at which it evaluates to 0, and at that point the matrix of partial derivatives with respect to the y variables is an invertible matrix. So with those assumptions, our goal then is to find a neighborhood v1 cross v2 of this point x bar y bar, and a C1 function that takes us from the first part of the neighborhood to the second part of the neighborhood, such that these conditions hold, that we have zeros in this neighborhood exactly when we can solve for the y variables in terms of the x variables. And then finally, even if we don't explicitly know what the phi function is, we can calculate what the derivative of phi is in this way. So we want to prove that formula as well. All right, so let's get to it. So here is the beginning of the proof. So the proof is not going to be so long at all, as we're about to see, thanks to our utilization of the inverse function theorem. So we'll see how we can employ it in just a moment. So to that end, really, what we're going to do is we're going to start by defining this new function f plus, which takes the same input space, u, and now we're going to Rn as the output space. And the way that it works, so f plus is defined in this way here, where the bottom portion of the vector is still the same function f, but now the top portion, so we're padding it with the x vectors. Okay, so x, remember, that part had n minus m components. So we have x1 all the way to xn minus m. So all those entries appear here, and then you have the f function outputs. So you're just padding the function f with extra components, and hence we call it f plus. And the purpose is that now your input space and output space are the same size. So now let's take the derivative of this function. So the derivative of f plus is given here by this matrix. So let's just scroll back up here for a moment. Here we're writing it in block form. So here's one block, another block, and another block of the overall matrix. The way that you can visualize this is that this part here, this division that is, this is corresponding to the x variables, and then over here is corresponding to the y variables. So we have x1 all the way to xn minus m, and then y1 all the way to ym. Those are the variables which we're differentiating with respect to. And then this division here, this is corresponding to all the function outputs. So here we have that the top part is corresponding to the differentiation with respect to this top part, and the bottom part is corresponding to the differentiation of this bottom part of the function. So then overall, here in this block, we are taking the derivative of this portion of the function with respect to the x variables. And then similarly here, the derivative of this portion of the function with respect to the y variables is going to be 0, because, the x and y variables are independent of each other. And then down here in the bottom part, which is corresponding to this function, well, first you differentiate with respect to the x variables, and then you differentiate with respect to the y variables. Now, by the block structure of this matrix, what we have here is it's a 2x2 block system that we have here, and the main diagonal blocks, which are here and here, are both invertible, at least specifically at the point x bar y bar. So that's what we're saying down here. When you plug in x bar y bar, by hypothesis, this part is invertible, and then obviously the identity matrix is invertible. And then this part is a bunch of zeros. So when you have a matrix of that structure where these parts are invertible and this part is zeros, then it doesn't even matter what this block is. We already have enough to infer that the overall matrix is invertible. That's just a fact about matrices of this particular structure. If you're unfamiliar with that fact and you want to see a detailed proof on it, then refer to the supplemental video on this video for that proof. But in any case, what we have here is that we are now guaranteed to have an invertible matrix at the point x bar y bar. So then what the inverse function theorem tells us when we have an invertible derivative is that there exist neighborhoods around that point, so v around x bar y bar and w around the image of x bar y bar, which is this, and a local C1 inverse, which we're calling G, which takes us back from W back to V. And V here, by the way, that's V1 cross V2, just to indicate that V1 is the part around X bar and V2 is the part around Y bar. So this is V. And this function is the inverse of f plus locally around this point x bar y bar. So with this information, what you do is you can define a function phi from v1 to v2 in this way. So this is an indirect description of the function phi, but it does unambiguously define it. So what is this formula saying here? Well, if you take this overall vector, x phi of x, what we want it to be equal to is this vector here, which we already know what it is. G of x0 is saying that it is, because it's the inverse of f plus, then g of x0 is saying this is the point such that when you plug it in to f plus, you get the output of x0. That's just by definition what the inverse is. So whatever the vector is, such that when you plug it into f plus, you get x0, that is the vector for which we are setting x phi of x equal to it. Okay, so by definition of g, this is going to be some point xy. And so, of course, the x matches up with this x here, and then this y is going to be what phi of x is set equal to. And so that is how we indirectly are defining phi of x. Now, does this make sense? Let's just think here for a moment. For each x in v1, there's going to be a unique y in v2 such that this property holds, that f plus of xy equals x0. So let's just say, for contradiction, we were to take, f plus of xy1, and let's say that equaled x0, and then also we took f plus of xy2, and that also equaled this same x0 here. Well, that can't happen because we're guaranteed to have local invertibility. So in particular, that means that f plus and g on this region are 1-to-1. So there can't be 2 points which both get mapped to the same output. So there can only be a unique point. Let's say it's this one for which it gets mapped to x0. And so therefore, this y would be the phi of x for this particular x. Okay, so just by the structure of this statement, going back here, for each x, there exists a unique y. So that means that we're defining this y to be the phi of this x here. All right, so we have our neighborhood, v1 cross v2, and we have our function phi, which goes from v1 to v2. Now let's make sure they satisfy the appropriate properties. Well, first of all, let's just take note of the fact that since g is c1, which is guaranteed by the inverse function theorem, then phi is also c1, because, again, phi is being defined in terms of g. So here is g, and then phi is defined in terms of that. So the c1 property carries through that way. So that satisfies one of the conclusions that we wanted to have about the implicit function theorem. And now, let's just go back to the top for a moment, just to refer back to what we want. What we want to show is that y equals phi of x exactly when we have this happening here, that x and y are in their respective parts of the neighborhood, and there is 0 of the function. So let's prove that if and only if then. So going in this direction, we're supposing that we have a 0 of the function in the neighborhood. Then using the fact that f plus of xy would be x0 then, because by definition you just always start with the x, and then this 0 is this 0 here. What that does for us is that implies that if you take g of both sides in this neighborhood, so you take g of this and you take g of this, that, the g and the f plus cancel, just leaving you with xy equals g of x0. And by definition, we defined this component to be phi of x. And so that is what we see here. And in the other direction, if we're starting by supposing that y equals phi of x, then what we have is that, if you were to consider this vector here, this is, x and then f of x phi of x, which is xy, by the way, but here y equals phi of x. So that is equal to f plus of x phi of x by definition of what f plus is. And then by definition of what phi of x is, this is forced to be equal to x0. Because again, we're saying that phi of x is the unique coordinate that you can plug in here such that when you take f plus of it, you get x0. And so since we do have phi of x here, you do get x0. And so therefore, in particular, as you can see, we have that this part, f of x phi of x equals 0. And that is what appears down here. So we've satisfied that part too, and that proves the biconditional statement. Now that we've proven the biconditional, the final thing that we need to do, if we go back up here, is we need to demonstrate this formula is true. And so to that end, what we're going to do is we'll come over here and we'll do a calculation and get a derivation for the derivative of the phi function. So first of all, what we're going to do is first make note of the fact that we have f of x phi of x equals 0. That's specifically for the x's that are in their respective part of the neighborhood, and just by the definition of what phi is. Okay, so that means that if we were to calculate the derivative of f, we would also get 0, just like this. So we have that, that 0 is the derivative of f, and now what we're going to do is we are going to just calculate in general what the derivative of f is. Okay, so first of all, to be explicit about things, we should write out, we're going to define h of x to be equal to x phi of x. That way, what we're doing here is we're calculating the derivative of f composed with h of x. And the reason for writing it out like that is just to be explicit about the fact that we're using the chain rule for differentiation. So that works just as well in the multivariable setting. And so this equals the derivative of f at h of x multiplied by the derivative of h of x. First of all, let's just calculate this derivative of h of x. Well, we have that h of x is kind of expressed in a block form here. It's a block vector. So let's write the derivative as a block matrix. So what we'll do is we will have something like this, where two parts, the first block will correspond to the derivative of this part, and the second block will correspond to the derivative of this part. And let's keep in mind that h only depends on the x variables, so we're only differentiating with respect to x variables here. So the derivative of x with respect to the x variables, well, that's just going to give you an identity matrix, because you're differentiating each individual x variable with respect to itself. That'll give you 1s on the diagonal, and then everywhere else you'll have 0s, since all the x's are independent from each other. And then when we're calculating the derivative of phi of x, well, it's just whatever that is, so the derivative of phi of x. So we have this matrix here for the derivative of h. Now let's calculate in a similar way what the derivative of f is. We're going to do it in a way that matches the format, or is of analogous format to the block matrix on the right here. So we're going to make this a block matrix of this form, where on the left we have the derivative of f with respect to the x variables, and evaluated at h of x, of course. And then next, the derivative of f with respect to the y variables, again, at h of x. The reason for writing it out like that is just to make it clear how this multiplication is going to work, because if you know how matrix algebra works, you're going to recognize that you can just multiply these blocks together as if they were entries of vectors. So it'll be this times this plus this times this. Just working that multiplication out, what we have is this equals the derivative of f by x at h of x. And you know what, we'll replace the h of x now with what it is, which is x phi of x, multiplied by the identity, plus the derivative of f by the y variables, again at x phi of x, and then multiplied by the derivative of phi of x. So you can notice now that we do have our derivative of phi of x. The point is that if we trace all the way back up to the top here, what we have is that this equals 0. And so what we can do is we can effectively isolate for the derivative of phi of x and hence solve for it and get the formula that we saw in the theorem. So we'll just say this implies that, that if we just subtract, first of all, let's just subtract this from both sides. So we have negative derivative of f with respect to x at x phi of x. And then that's going to equal derivative of f with respect to y at x phi of x, and multiplied by the derivative of phi of x. And then what we can do is we can multiply by the inverse of this matrix on the left. Now the question is, can we do that in general? What we know is from our hypotheses up here, we know that the derivative of f with respect to the y variables at specifically at x bar y bar is invertible. But how about at a more general point in that local neighborhood? And the answer is yes, it is. It is invertible because when we come back to the derivative of the f plus function, we have this. And we said that because this and this were invertible at x bar y bar, then the entire thing here was invertible. Also, we had zeros here. But anyways, because that was invertible, then we invoked the inverse function theorem, and that guarantees us that we will have invertibility of this matrix in some local region. So it's not just at this point x bar y bar, but in fact it's in this more general neighborhood v and w. Because in particular, if you remember what the inverse function theorem says, if we just put some space here, it says that the derivative of the inverse function, which is g, evaluated at some image point, which we'll call f plus of xy, that's equal to the derivative of f plus at xy inverse. So in other words, the derivative of the inverse equals the inverse of the derivative. But the point is that this matrix here is invertible. So what is this matrix? Well, if we just go back one more time over here, that's this matrix here is invertible. Now, does this overall matrix being invertible imply that these respective blocks are invertible? And the answer is yes, it does. So that's just, again, another structural property of a matrix of this form. So this total thing is invertible if and only if this and this are both invertible. So because the inverse function theorem tells us that this is invertible on some local region, then we can infer that this is also invertible on that same local region. And the phi of x function is going to, by definition, be inside that local region for us, and hence this part here, which appears over here, this is invertible. So it does make sense then to multiply by the inverse of that matrix. And so this implies ultimately that the derivative of phi of x is equal to multiplying by this inverse over here. We have that it's the derivative of f by the y variables at x phi of x inverse. And then we have multiplied by the derivative of f by the x variables, again, at x phi of x. And then don't forget about the minus sign, which appeared right here. And so ultimately what we see is that this formula right here is what we wanted to prove. And so that concludes the proof of the implicit function theorem. So before we wrap up, we will go back to the slides and we'll take a look at some more examples that will illustrate the utility of the implicit function theorem and how we might use it in practice. Now that we have a more thorough understanding of the implicit function theorem, let's see how we might apply it in a setting that is slightly more realistic in terms of what you might see in quotes real life. So here's an example from the excellent textbook Multivariable Mathematics by Schifrin. We'll take a look at exercise 6.2.4. So it's as follows. We're going to show that the equations defined by x squared y plus xy squared plus t squared minus 1 being equal to 0 and x squared plus y squared minus 2yt being equal to 0, those two equations together define x and y implicitly as C1 functions of t near the point xyt being minus 1, 1, 1. And then so we'll show that and then find the tangent line at this point to the curve so defined. Meaning that when you consider the common zeros of these two equations, this is going to define some curve in 3D space, and we want to find the tangent to that curve at this point, minus 1, 1, 1. Really, it might be worth taking a shot at this yourself. It's a straightforward application of the theorem, but if you are just here for the show, then let's get on with the solution. We're going to, of course, apply the implicit function theorem to this function. So the function capital F of these three variables, x, y, t, is going to be given by the outputs, of course, given by these two equations. And then we're setting that equal to 0. So in other words, we're setting each component equal to 0, of course, as it's suggested here as well. We should note that minus 1, 1, 1 is a root of this function. Well, how does the application of the theorem work? We're going to see if we can't solve for x and y in terms of t, and the implicit function theorem tells us how we can test that. What you do is you take the derivative of this function, which in this case is going to be this 2 by 3 matrix here. So 2 rows for 2 equations, 3 variables that we are taking partials with respect to. And then we're going to plug in this point, minus 1, 1, 1, and that gives us this matrix here. So this is the derivative of the function at this point. And what we need to check is that the submatrix that is indexed by the variables x and y, that is the variables that we want to solve for, is an invertible submatrix. So here's that matrix, and as you can see, the determinant is going to be non-zero, and hence it is invertible. Then what that means by the implicit function theorem is that we can solve for x and y in terms of some function of t, and in particular a C1 function of t. So we will be satisfying this C1 property by the implicit function theorem. As we typically denote it, the function is phi, which here is going to be broken into two components, phi1 and phi2, for each of the two variables x and y respectively. And so this implies that the curve defined by setting this function f equal to 0 around this point is given here. So here's the x component, the y component, and the t component. But of course, now since we know that x and y are given in terms of t, we now have a curve that is completely parametrized by t. This is good because we know how to find the tangent of a parametrized curve. So the tangent vector is going to be the derivative of this curve differentiated with respect to the parameter, which is t. And then we're going to plug in t equals 1 because that's the t coordinate of the point that we're concerned with. That gives us our tangent vector, and so then the tangent line is going to be this point, which is the point that we're concerned with, minus 1, 1, 1, plus a scalar r times the tangent vector. So this vector here that you see is the tangent vector, and we've plugged in t equals 1 into the parameter. So now, if we only knew what phi prime evaluated at this point t equals 1 was, then we would explicitly have our tangent line. But the implicit function theorem, of course, gives us a formula for determining that. So we know by the implicit function theorem that the derivative of phi at the particular point that we're concerned with, which is t equals 1, is given by this formula here. So it's minus the inverse of the submatrix of partial derivatives with respect to the variables that we want to solve for, which are x and y in this case. So we're taking that submatrix, evaluated at our point, and then multiplying it by the partial with respect to the variables that we are solving in terms of, which in this case is t, and again evaluated at the point minus 1, 1, 1. So in this case, you have the inverse of this matrix up here. This is with respect to the x and y variables, and you take the inverse of that, negate it, and then multiply it by this remaining submatrix here. And as you can see down here, that will give you this concrete vector, minus 1, 3. So that means we can go back and fill in this value here for our derivative. So the tangent line then is going to be the point that we're concerned with, minus 1, 1, 1, plus a scalar r times the tangent vector, which we've now concretely determined to be minus 1, 3, and then the 1 that we already had. So there we go. This is the equation of the tangent line in 3D space for the curve that was implicitly defined by setting this function capital F equal to 0. So nothing too groundbreaking once you have taken the implicit function theorem for granted, but if you just think about trying to solve this problem without having access to the implicit function theorem, it would almost be hopeless. So it's just interesting to think that we can say something notable about this system of equations without ever having actually explicitly solved for it. So this is one type of interesting application of the implicit function theorem. Before we wrap up the video, we will go on to take a look at one more particularly notable application of the theorem. So finally, we are going to take a look at implicit differentiation in retrospect. So by in retrospect, what I'm really referring to here is the fact that we're typically introduced to implicit differentiation in an introductory calculus class. But at that time, we're not really prepared to understand why we are able to do implicit differentiation legally. So let's just take a look at a very typical example that you would see in a calculus class. So consider the unit circle, x squared plus y squared equals 1. So here it is over here. Well, what is the slope of the tangent line, for example, at this point here, a half root 3 over 2, so that's just one of the standard points that you're concerned with on the unit circle when you start becoming concerned with trigonometry. So, you know, it's roughly here-ish on the unit circle. And so geometrically, it makes sense to ask this question because here it would be the blue tangent line, and so clearly it exists and it has some slope. So we should be able, in principle, to figure out what that is, given that all we need to know is the unit circle and the particular point that we're concerned with. And we know the algebraic equation for the unit circle, it's here, and we know the point that we're concerned with, it's here. So what we do in introductory calculus is we differentiate with respect to x both sides. And so the way that would work is that you take the derivative of x squared is 2x, the derivative of y squared is 2y, and then we say times by the chain rule dy by dx. And then the derivative with respect to x of a constant is 0. So you get this equation here. Then dy by dx is already here and ready to be solved for, so we just solve for it in the normal way, and we get that dy by dx equals negative x over y. And so in particular, if we're concerned with this point xy, then it would be negative a half over root 3 over 2, or negative root 3 over 3, which is approximately negative 0.577. So that's the slope, and in fact we can do one better. We can actually figure out the equation of that blue line. It's just using the point slope form of the equation of a line. So the point is root 3, 2 for the y coordinate and a half for the x coordinate, and then here is the slope. And that is how you would go about solving this sort of question in an introductory calculus class. Of course, the question becomes, why was this justified? So when I first took a course in calculus, it seemed so forced on us that we were able to simply say 2y times dy by dx, as if it was just understood that y could be expressed as a function of x. And this did not sit well with me, because it does just seem to come out of nowhere with no real justification in consideration. Of course, this being an introductory calculus class, we weren't exposed to the implicit function theorem, but that is exactly what you need in order to justify implicit differentiation. So just to come back to this question, why was it justified? It's by the implicit function theorem. The way that it works is, in this example, you would take the function of two variables, x and y, to be x squared plus y squared minus 1, and we are looking for the zeros of that function. Of course, that's the set where x squared plus y squared equals 1, which is, in other words, the unit circle. And so we're asking, can we actually express this variable y in terms of this other variable x? And the implicit function theorem is able to answer that for us. What it says is that, well, if you take the derivative and you consider the submatrix corresponding to the variables that you want to solve for, which in this case would just be the y component here, as long as that's invertible, then you can solve for this variable in terms of the other variables, which in this case would just be x. And so here, what we have is that y can be locally expressed as some function of x if and only if the submatrix of this overall matrix indexed by y is invertible, and since the submatrix is a 1-by-1 matrix, which is just this number 2y, this is if and only if y is non-zero. And going back to the particular point that we are just arbitrarily concerned with here, 1/2 root 3 over 2, here, of course, the y-coordinate is non-zero, and so this condition is satisfied, and we can solve for y locally in terms of some function of x. So by that reasoning, it actually is justified to use the chain rule on this y squared term that shows up in the equation for the unit circle, because the implicit function theorem guarantees us that y is a function of x. And so the chain rule really does apply in the way that it was asserted to us that it did in our introductory calculus class. Now, in this particular example, it's worth noting that not only is y some implicit function of x, we can actually explicitly solve for y in terms of x. Of course, what you do is you just move the x squared term to the other side, and you take the square root of the y squared, which will give you y equals either plus or minus the square root of 1 minus x squared. Of course, that plus or minus is the entire point of the cautionary caveat of needing to take a local function y of x. Because if you were to say, consider a point on the unit circle, say over here, well, this sort of point is still going to have some region on which you can express y as a function of x, and in particular, y would be the positive square root of 1 minus x squared. But if we were to come over here, then all of a sudden we would have some local neighborhood on which y would be expressed as the negative square root of 1 minus x squared. And so the function is going to be different depending on the point that you take. And that is a point that we need to consider more generally, but this simple example already illustrates why we need to make that local consideration, because there's no single function that will express y in terms of x on this entire unit circle. So anyways, now we have a sharper understanding of why and when we are able to perform implicit differentiation. And the answer is not because your calculus teacher or textbook simply told you so, but rather it's because of this theorem that was behind the scenes the entire time. So calculus is one of these slippery subjects that sometimes everything is completely justified and sometimes things are just asserted at you as true. I've never been a fan of this, but this is how it is. But if nothing else, if you continue onwards, you do get that retrospective enlightenment that will make you appreciate the subject all that much more later on. So this theorem, being a pretty fundamental theorem in higher math, of course there's going to be more that we could say about this theorem, but we'll have to leave it here for the sake of concluding this video. But if you've made it this far, hopefully you've taken away the main idea of this theorem and what it can be used for, and it will serve you well in your future math endeavors. And so if you have been watching, thank you very much. See you in future videos.